This is another example on fixed beam using consistent deformation method. The question is given as analyze the fixed beam using consistent deformation method. Draw shear force diagram, bending moment diagram and elastic curve. So there is a fixed beam on which a point load of 5 kilonewtons is acting, and the distances are 1 meter and 3 meters, and these points are given as point A, B, C, and EI is given as constant. So we have to analyze this beam using consistent deformation method and draw SFD, BMD and elastic curve. So here we have two equations to be used to find two redundants. So that is given as theta due to loads plus theta due to redundants is equal to 0, where theta can be written as area of BMD divided by EI. And the other compatibility equation is deflection due to loads plus deflection due to redundants is equal to total settlement of supports, and deflection is written as area of BMD divided by EI multiplied by centroidal distance. Now here let us choose the redundants as reaction at B and moment at B. The direction is up to you, and this can be divided into cantilever with point load 5 kilonewton, 1 meter, 3 meters, and it can be cantilever with RB 4 meters, and one more beam will be cantilever with moment MB. The span is 4 meters. Now the bending moment diagram for cantilever with 5 kilonewton load will be a hogging BMD with triangular variation, and the moment at A will be 5 into 1, that is 5 kilonewton meter, and this will be hogging. These are the points A, B, C. And for cantilever with RB, we get a sagging bending moment diagram. So this is positive, and the bending moment at A will be 4 times RB, and the bending moment diagram for cantilever with end moment will be a hogging BMD. This is MB, which is uniform, and this will be negative. So this is point A, point B, this is point A and point B. And the centroidal distances should be considered from the centroid till the redundants, from the centroid till the redundants for all the BMDs. So these are the centroidal distances. Now we can apply our compatibility equations. So applying the first compatibility equation, that is slope due to loads plus slope due to redundance is equal to 0, and slope is given as area of BMD divided by EI. So for the first BMD here, the area of BMD is minus half into, this is 1 meter, this is 3 meters, so half into base into height divided by EI, and for this it is plus, the base is 4 meters, area will be half into 4 into 4 RB divided by EI, and this will be minus 4 into, that is base into height, that is 4 into MB, which is equal to 0. So on simplifying this, there is divide by EI here, so I can take 1 by EI and send it to the right side, so it will get cancelled. So if I simplify this equation, I will get 8RB minus 4MB is equal to 2.5, and if I solve this equation, I will get the value, sorry, let us call this equation as equation 1. So here we have two unknowns, RB and MB. So this is the first equation. Now we can apply the second compatibility equation for each of the BMD, and we know it is area of BMD into centroidal distance. So for the first BMD, this will be minus half into base into height divided by EI, and the centroidal distance will be 2/3 of 1 plus 3 meters. For second BMD, it will be plus half into base into height divided by EI, and the centroidal distance will be 2/3 of 4, and for the third BMD it will be minus, area will be 4 into MB divided by EI, and the centroidal distance will be half of 4. This is equal to, here there is no settlement given for the supports, so we can take this value as 0. This will be equated to 0. Now if we simplify this equation, we will get minus 9.17 plus 21.33 RB minus 8 MB is equal to 0, or I can write this equation as 21.33 RB minus 8 MB is equal to 9.17. So this is my equation 2. again with two unknowns, R, B and MB. So we have here two equations with two unknowns. So we can solve these equations to find R, B and MB. So for the first equation, it is 8 minus 4 and 2.5. And for the second equation, it is 21.33 minus 8 and 9.17. So here solving equations 1 and 2, we get RB as 0.78 kilonewtons and MB as 0.94 kilonewton meter. These are the two redundants that we have determined. So here we have a fixed beam on which there is a point load 5 kilonewtons. The span is 1 meter and 3 meters. This is point A, B and C. So now we have determined the redundants. RB as 0.78 kilonewtons and this moment is plus 0.94. That means whatever direction we have assumed here for MB is the correct direction. So we have a clockwise moment here of 0.94 kilonewton meter, which is the value of MB. So these are the two redundants. Now we can make use of static equilibrium equations. Summation V is equal to 0 and we can calculate the vertical reaction at A. So let us consider the reaction at A is RA. So this will be RA plus 0.78 is equal to 5. So from this equation, we get the value of RA as 4.22 kilonewtons. So this is the reaction at A. So this reaction is 4.22 kilonewtons. So now we know the two reactions. So we can draw the shear force diagram in kilonewtons. This is our reference. At A, there is an upward shear force of 4.22. From point A to C, it is constant. At C, there is downward 5. So it will be 4.22 minus 5, that is minus 0.78. And from point C to B, it will be constant. And at point B, there is an upward reaction of 0.78. So it becomes 0. This is positive, this is negative. So this is the shear force diagram, which is drawn from left to right with upward forces positive and downward forces negative. To draw BMD, we have to calculate bending moments at various points. And let us consider the sign convention, sagging bending moments positive. So we already know that the moment at B is hogging 0.94. So that is minus 0.94 kilonewton meter. So we want moment at C. If I consider right hand side, so this will be hogging 0.94 and 0.78 into 3, which is sagging. So this is plus 0.78 into 3. This is calculated as 1.4 kilonewton meter. And moment at A, if we consider right hand side, will be, this is hogging 0.94 and 0.78 into 4 meters sagging, that is 0.78 into 4, and 5 into 1, this is hogging, so it is minus 5 into 1. So this will be minus 2.82 kilonewton meter. So now we know the bending moments at various points. So we can draw the BMD in kilonewton meter. So this is our reference. Moment at B is hogging 0.94. So it is below the reference. Moment at C is 1.4. So it is positive 1.4. And moment at A is hogging minus 2.82. So it will be below the reference 2.82. And because it is only a point load, you can join all these points using straight lines. Above the reference will be positive, below the reference is negative. And if required, these points of contraflexures can be calculated by making use of similar triangles. This is point of contraflexure. Right, and the elastic curve will be for the given fixed beam from point A till the point of contraflexure. It is hogging, so this region has to hog. From this point till here it is sagging, so it has to sag, and from this point till point B it is hogging, so it has to hog again. And these are the points of contraflexure. This is the elastic curve. So this is the second example in fixed beams. Keep following for more examples.